So, as we mentioned earlier, there's kind of this progression of programming model characteristics from over-decomposition to migratability and then adaptivity. So we've covered over-decomposition at length. Just to give you the brief on migratability. So we have this mechanism in CHARM for object serialization and actually general data serialization called FUP, which is the pack-unpack framework. This is the way that we move objects around. It's actually also the way that we serialize arguments to entry methods. So essentially all it's doing is it's providing a way to take bits in memory, the way your program is going to operate on them, serialize them into bits that would go out onto the wire as a linear buffer, and then how do you convert them back to bits in memory that your program can operate on again. So for an object that's being migrated, there's kind of this life cycle that the object goes through, where at initial construction, I've got the pointer, here we go. So at initial construction, you get your constructor call with your standard arguments that you'd use to initialize the object. And then it's going to go through this lifetime of methods being invoked. And then at some point, if you turn on load balancing or if you have a checkpoint happening, then the runtime is going to go through the migration flow for this. So it's going to tell the object, it's going to call this virtual method about to migrate, and normally that doesn't actually need to do anything. Sometimes in really complicated applications, you might release a reference to a cached value somewhere on your processor or things like that. Then it will size the application, so it will figure out how much data there is to be serialized. It will allocate a buffer for that, pack the data into that buffer, and then it will call if it's actually migrating the object rather than just checkpointing it, it'll call the destructor. And then on the receiving side, if an object is immigrating to a processor or is being restored from a checkpoint, then that's where that CK migrate message constructor gets called. So that is essentially a dummy constructor that doesn't need to do anything because anything it initializes is immediately going to be overwritten in the unpack from the serialized data. So you get that migration constructor which you do as little as possible because we're going to unpack over anything that it wrote. And then there's this separate call to say, okay, I've finished unpacking you. If you need to do anything to move into your new home, pick up local references to other objects or things like that, you can do that there. So the way this works, here's just an example char with some elements, with some members in it, an int, a float, a character, and an array of a few more floats. So the way the PUP framework works is for char classes, because we have some of this runtime generated state that needs to travel with the object, we have to tell that inherited state, yes, pack yourself up as well. We're working on things to eliminate that, but the implementation's kind of complex. And then for each of the individual members, we have this pupper object that the runtime system is going to pass in. And we just pass each of those members into it. And we use the pipe symbol here kind of to be reminiscent of the pipe in a shell script, that you're just pushing data through a pipeline. For objects that are not, that are non-scalar, so like this array, we pass the array and the size of it, and this is overloaded for any type that it knows how to serialize, so it can pick up the entire vector of data rather than just one element. And these pub methods can be defined for chars. If you have your own data types that you want to pass in arguments, again, you can just pick them up and use them automatically.
Sorry, just to be clear.
Yeah.
If you want to have migratability, you have to write a pub.
Yes. If you want to have
user stuff.
Yes. If you want migratability, you have to write a pub for the things to be migrated.
You can't screw it up.
That's pretty straightforward.
Well, no. Glad means that the other way around. If if you get the pup wrong, funny things will happen in your code. Funny, scary, confusing, all sorts of terrible things can happen in your code. So yes, they look simple, but it's someplace where we don't really have a good way to error check. We don't have, a nice mechanism to say, oh, you got that wrong, you're missing something, things are inconsistent.
Do you have to send everything in the object, or can you select?
You can select.
But if you select wrongly, you'd be sorry.
Well, yeah. So if your objects are only migrating at particular points in their life cycle, where the object might have transient state, but at the migration points that transient state is dead, then yes, you would want to leave out that transient state from what you serialize.
Is there a way just to say, hey, treat this as a bag of bytes. I've got a homogeneous processor. Just ship it. I don't care. You're not going to screw it up.
Yes, there is. There is a method, or there's a declaration, PUP bytes.
Oh, good.
That just says, treat this object as a bag of bytes, serialize it, size up from beginning to end, and it's fine.
Good. We'll call it. That's it. So that's going to screw up that.
Well, that doesn't work for chars specifically because you have to deal with the base class object, unfortunately.
So you could pup a whole tree then. Like if you had a complex data structure inside.
Yeah. Yes. Yeah, exactly. And I believe our slightly deeper example has exactly that kind of thing.
Okay.
So I think we have utility classes that make this easier. They haven't made it into our tutorial material. But essentially, so what we have is we have some variable array of a given size of floats. So in our pup routine, we pack or unpack the size deterministically. And then we say, OK, if we're on the unpacking end, then we need to actually allocate memory for space in which to unpack the data that we're receiving. So then, regardless of which direction we're going, packing or unpacking, we want to actually pack the contents of that array, so the pointer to it and its size. And then for this other thing, which we're just going to have either one instance of or none, we look at whether it's a null pointer, pack up that Boolean flag, and if it's not null and we're in the unpacking case, meaning that we have to deallocate it, or we have to allocate it, then we allocate the new instance on the receiving side, and then pack or unpack the content.
So the vertical bar packs or unpacks?
Sorry, what was the question?
The pipe bar thing? It sort of knows.
Yeah.
It's
so the
unpacking flag.
The pupper object itself knows which direction it's going, whether it's packing or unpacking. So the idea in this is that pup methods should mostly be uniform, and in particular, they need to have the same sequence of objects being packed or unpacked, so that you end up with the right bits of the buffer ending up in the right fields of the object.
Or do we have to take care? So if we migrate the char new to the class, do we delete our local instance, or does the whole char?
So when a char is migrated off a processor, the runtime system will call delete on that char.
Okay.
And so the destructor should then do that deallocation.
Okay.
So that's why you don't see any deletes in the packing code. So as mentioned before, if you get the pup wrong, say you've added a new field. Yeah, sure.
I mean, in this case, let's say you're unpacking.
Yeah.
So you get the heap array size with the vertical bar.
Yep.
And further below, you call it with the size and the array.
Meaning here.
Yeah. And yet this thing, it knows it's unpacking.
Yeah.
But it cannot do the allocation for you internally.
So it doesn't necessarily know how you want it allocated. You might decide, you might have a special heap that you want to put it on. You might have a buffer someplace else. So it's
being more flexible.
Yeah. I mean, it requires the programmer to be more explicit about it, but it means that if you do something different from like the very basic thing, it's not going to step on your toes. So as noted, if you're adding or removing, typically it's only a problem with adding, because if you remove a member, the compiler will error on the missing field. But if you add stuff, we don't really have a good way to say you missed something. Keep in mind that this is essentially all passed by value. So if you have a recursive structure on the heap, you need to actually go through it recursively. If you implement the PUP methods nicely, they should kind of do that recursion naturally. Yeah, you've seen the memory allocation on unpacking. You have to make sure, because the same framework is doing sizing, packing, and unpacking, you have to make sure that all the variables get touched consistently. That's why we have things like flags. And typically, when you want to test your application to see whether object migration is behaving sensibly or not, we have this special load balancer rotate LB. What that will do is it will take every object on every processor and shift them cyclically to the next processor in the job, so that every object migrates every time that's invoked.
You also use random.
Yeah, then there's also a randomizing load balancer that'll just kind of shuffle things, but it's less certain to migrate. If you have something that only shows up with like an uninitialized value or something like that, you're lowering your probability.
Yeah, and LB is easier to predict, right? You know that if something where things should be after the shift.
There are, you can tell it not to migrate your char under any circumstance.
Yes. Yeah, so if you have a char that shouldn't migrate, you can set a flag in the char saying this isn't migratable either right now or ever, and the runtime will respect that.
Sorry, did you show us the sizing?
It's the same code. Popper is polymorphic. The runtime will pass a sizing popper first, which will examine everything, but it won't actually touch the data. It'll just sum up the size of everything that it was passed. Then the runtime will see, okay, I finished sizing it. What was the total at the end? Allocate that buffer, inside a packing pupper, or give it to a packing pupper. Then it will do the same thing packing into that buffer that was just allocated. So that's one of the niceties of this framework, that you write one piece of code for every step of the serialization, deserialization process. Does that make sense?
Yep.
Okay. Okay. So just as an application of this, without getting into any of the deeper runtime system stuff, once you have objects that can migrate, the runtime system can implement fault tolerance for you automatically. So there are 4 different approaches, and with some sub-variations within these, of how the runtime system can do automatic fault tolerance. So the most straightforward, and the one that we're going to discuss details of, is disk-based checkpoint restart. So that's the same as if your application code were to write out manual checkpoint files, and this saves you from whole machine failures, end of job, timeout, whatever. There are also online fault tolerance mechanisms that we're not going to go into detail on, but just know that they exist if you want to experiment with them, or if you want to convince data center operators that they should not kill jobs when a node goes down so that you can take advantage of this. That would be great. But the common feature of all of these is that checkpointing is a single function call that's essentially transparent to the application logic. They all leverage the object migration capability. Once you know how to put an object on the wire, you know how to put it in a file as well. And they can be used in concert with load balancing as well. So just for the simple checkpoint to file system case, imagine you have a job allocation that gives you 5 hours of execution time, and you know that your total simulation is going to take much more than 5 hours. Maybe it takes a week. So all you need to do is, at some regular interval during your run, or now on Blue Waters, they're actually adding a signal mechanism to say, your job ends in 15 minutes, and it's possible actually to submit killable jobs on Blue Waters. So it will tell you, I'm going to kill you in 15 minutes because I want your nodes back. You can trigger a checkpoint, and what this will do is it will migrate all of the chars to a buffer that will end up in files on the persistent file system. So on the NFS, Lustre, GPFS, whatever system. So you find a convenient synchronization point in your application. You quiet down all the work. You set up a callback for what to do when you resume from this checkpoint, either as execution continues or when you restart. And you say checkpoint to files in a directory with this name. And so then when you're running, when you want to restart, you start your program as normal, and then you add this extra runtime flag plus restart. And this log here is a placeholder. So since we were asked to call that out. So that is the name of whatever directory you stuck the checkpoint in. You say, my checkpoint files are in that directory. Resume execution from wherever that left off. And one neat feature of this is that Charm++ can actually resume on different numbers of processors than you checkpointed on. So there's no constraint of, there's no runtime level constraint of, you know, I was running it on 2,000 processors before, I need to get an allocation of exactly that many when I resume. If you see, oh, hey, there's 1,900 processors available right now in backfill for the next 8 hours, you just grab them and start running immediately, rather than having to wait in the queue for a bigger slice.
Does the checkpoint work on BlueGene queue as well?
Yeah. Yeah. So this style of checkpoint is architecture independent. Okay. It works everywhere as long as you have a file system to put it on. That's the only dependence.
It's one file.
It's a direct. It's one file per PE.
Per PE. Okay.
Or actually, well, it's
per node or core or.
It's a little bit more than one file per PE because we have arrays and other runtime structures as well. But
that you'll.
Yeah. But it's self-contained in this directory, and it's something. Have your flight to catch?
Yeah.
Okay. Well, have a safe
really
trip.
helpful.
Thank you for coming.
Send you an email with the puzzle.
Great.
So that will be extended for when machines have flash memory and things like this.
Yeah. So we have So another important point here is we can optimize this in the runtime system for any kind of development, so architecture-wise, file system-wise, whatever, and the application logic is still just make this function call.
That's one of the good things of learning all this syntax. You get the good.
Yeah.
So, like, what do you have to do as a programmer? I mean, like, the say hello. Like, is it any? What is that?
Oh yeah, sorry. So we kind of elided this. So essentially, this is just saying the same way we had reduction targets earlier. This is just saying find the hello method or the say hi method rather of the hello char class and invoke that on hello proxy after you resume. If there were no callback here, the way the application should be written or effectively would be written is you would write a checkpoint and then it would just hang. There would be nothing happening after it because the application needs to be quiet.
Yeah, after the checkpoint, where do we go? Right? If I'm running and I'm making a checkpoint, I need to do something afterward.
Yeah. Yeah, where does execution
says
continue?
What to do next. Similarly, when you resume from the checkpoint,
you're going the same place.
Right?
You just keep cranking along where you were, though.
But at the end of the checkpoint, you need to
restart.
Need to kick things off, right? Because what you've done is
you've
stored the control flow up to the making of the checkpoint. Right? You haven't stored what happens next because that hasn't happened yet.
Yeah. So start from.
Sorry, I'm not getting it.
Well, wait, Eric. Yeah. So start from your checkpointing and your job is stopping right there. So consider the restart case.
Yes.
So after you've restarted, there are no messages in the queues.
Yes.
The system is completely idle. So you need to tell the runtime system, what do I do after restart to resume execution, to crank the engine back up,
You
right?
didn't write all the messages in the queue?
No, so that's what I'm saying. When you reach this point, you should have no messages.
Oh.
Because you need to create a coordinated checkpoint. So you need a consistent state. So if there are arbitrary messages in queues, you're going to get some jumble. So I'm pretty sure we do, in fact, checkpoint queued messages, but it will be unpleasant for the developer to have to account for checkpointing in kind of arbitrary conditions.
I still don't get it.
So imagine you get to the end of a time step or an iteration in your calculation.
Okay.
You say, okay, everything.
It's like an MPI barrier. Everybody's
Yes.
just like, stop.
Yes, everyone's stopped. You know exactly what state everything is in.
Yeah.
So you say, that is the state that I'm going to checkpoint.
Okay.
Usually, you
And
do
then-
something like you call a reduction.
Yeah, no, okay. I
And
understand
then when
that.
the reduction is done, everybody's sort of in the same state, and then you say,
I see. So this is
What the
this is not arbitrarily flexible. You
Um,
can't be like, we're going to checkpoint now in the middle of this giant communication.
the other checkpoint mechanisms do, I believe, support doing that. Like the more sophisticated researchy ones.
Okay, I think I understand this kind of checkpointing where you really finish a cycle
Yeah,
and before the next cycle,
Yeah.
you checkpoint, and then so you have to start the next cycle.
yeah. So that callback is just saying, what message do I send to whom
Yeah.
to start the next cycle
Yeah.
after you resume from the checkpoint?
But I can't checkpoint in the middle of everything.
You shouldn't. You don't want to.
It's hard, okay.
It will be a stickier process.
But theoretically, it's possible because char++ is just message driven.
Yeah.
Right?
So
We'll
that
just
so
start sending the messages and get going after.
yeah. So the in-memory checkpointing scheme has a mechanism to transparently produce what's called a distributed snapshot, which says here are the set of messages before the snapshot, here are the messages after it. The snapshot is the state at exactly between those messages, and then everything else after that is, queued and stored as in-flight messages.
So you can do an asynchronous checkpoint.
Yes, that's more experimental code. So we're less confident of the stability of it, so we don't want to encourage new users to just say, oh yeah, I'm going to go use that, because we don't want to disappoint people. Under promise, over deliver. This checkpoint mechanism works.
Thank you.
So, as we've mentioned a bunch of times before, the execution in char++ is asynchronous. So you don't have any sort of guarantees on when messages will arrive, in which order they'll be executed, which helps for efficiency, but sometimes it makes things difficult to understand and program. For example, before we saw that example where we sent 10 messages and the last one was supposed to end computation. However, if that one got there first, we can base that on a function computation. So Structured Dagger is a construct in char++ that kind of, it basically easily allows the programmer to sort of restrict control flow to a pattern they may find more desirable or necessary in cases. So again, so far a char is a reactive entity, so it simply waits for a message, and then as soon as it gets a message, whatever that message happens to be, it executes it, regardless of whether the programmer wanted something else to execute first. Basically, another way of expressing the life cycle of a char is some chars we might want to keep truly reactive, so any message they receive, they respond to it at any time, and that's what we want. However, sometimes we want a certain ordering, or certain things will have to happen in a certain ordering, so you might need to complete one part of the computation before the next part can carry on, and modeling this is possible without SDAG, however, SDAG is meant to make it easier. So in this case, when computation depends on remote invocation and completion of other computation, we can model it using a DAG, or a directed acyclic graph. And we have the functionality in Charm to sort of encode that into the chars themselves. So we're going to go back to the Fibonacci example before, as we had before. And if you remember, each parent had 2 children it was waiting on. And once it got the results from both of those children, it would know its result of the subproblem and could then in turn respond to its parent. So we kind of had this weird extra control flow in the respond message where we had to keep count of how many responses we've had. And then once we've received the 2 responses we were waiting for, then we know, okay, we've got our final results, and we can send that back. And even for this rather simple case, it was a little bit of extra mechanism that we would like to hide and allow the programmer to make things a little more clear. So in this case, again, we have the same CI file. We just have our Fibonacci constructor, where again it takes the number it's computing, whether or not it's the root, and the location to send its results. And we have our entry method for responding with a value. And now we're going to define this in terms of, let's see.
This is the original.
Yes, this is the original. So again, here we have this, when we get a respond message, when we receive a value from one of our children, we explicitly need to go and say, okay, have we actually gotten all of our children's responses? Then we can continue. And again, this is a very simple example. You can imagine when there's much more things you're waiting on. For example, if you're doing a 3D Jacobi and you need to wait on responses from all 6 of your neighbors, this is just going to get messier and messier and involve you to write a bunch of basically code that does this kind of stuff. So if we consider the Fibonacci chart, if it's not a leaf, it creates 2 children, and when both children return results, it can compute its own result and send it up. This logic is hidden in flags and counters, but essentially the key here is that every Fibonacci chart has the same communication pattern. Create 2 chars, wait for 2 responses, send your own message. So it has like this template of the communication pattern it's supposed to have. So what we want to do is kind of capture this at a higher level in the code, so that's easier to read, easier to code, easier to understand. So with a little notational support, for example, we introduced Structured Dagger. So Structured Dagger adds some additional constructs to the CI file. So when we're defining these entry methods that chars can respond to, we now have some additional constructs. The first one we're going to introduce is the when construct. So the when construct basically says what a char will do when it receives a message. So it declares the actions to perform when the message is received. And then in sequence, it acts like a blocking receive. So in this case, we have some method defined. And the body of that method is saying, when we receive entry method 1 with whatever parameters, we'll execute block 2. And when we receive entry method 2 with some parameters, we'll execute block 3. Now these are sequenced, so if we receive entry method 2 before we receive entry method 1, this message is just going to get buffered at the char, and we'll wait to actually execute it until after we've done what needs to come first. So we're giving this explicit ordering that's easy to look at. You can look at this code and say, okay, first we're going to execute entry method 1, do whatever it does here, and then move on to entry method 2. So unlike before where we'd have unordered sends and we didn't really know what order they'd be executed in, now we can sort of constrain the ordering of events.
Sorry, this is a method inside of the class.
Yeah, this is actually going to be in the CI file. So this is an entry method, some entry method. So we can invoke this on a char remotely as we normally would. And basically the body of this says, okay, first wait to make sure you have an entry method 1 message. When you have that message, right? When you have this message, so when there exists a message in the queue that matches this pattern, basically, then we can go ahead and execute some chunk of code, and then again wait until you have something that matches entry method 2 with these parameters, and then execute the next block of code. So the serial construct is another Structured Dagger construct. This just executes a serial block of C++ code in the CI file.
Is the SDAG Fibonacci thing in the code tutorial examples?
Yes.
Okay, what's the name so people can look at it?
Fib SDAG.
Okay.
Yeah, so
if
there's...
you want to look at it while you're explaining.
Yes, there's a larger... So we're going to build towards basically converting the SDAG, or sorry, the Fibonacci example from using this explicit buffering of messages to using SDAG. So that example's in the repository. We'll be getting that on the slides, but if you want to take a look at it now, you can go ahead and do that. So the serial construct just says execute this block of code. It'll be executed without interruption preemption, just like the body of any other entry method. The syntax is just serial, followed by some optional string, and then the C++ C++ code you want executed. Optional string is just there. For example, if we've seen examples of projections plots before, and in projections plots, it tells you each different colored block, and there usually corresponds to an entry method, telling you, where time is spent. So now you can also label these serial blocks so you can see how much time is spent in each of these. And then serial blocks are just, they can access any members of the class they belong to, just like any other serial block of code in that class. So for example, here we have entry method one has some parameters, and its body is just a serial block that will first invoke a method on this proxy and then call some function. Here we have another example where we've given an explicit name to this serial block. But the key thing to note here is that these methods right here, as they're defined right here, will behave exactly like methods in Charm++ already behave. So when you receive a method one invocation, in serial, just send a message, call a function, or over here, set a value. So where we really get the power of SDAG is when we combine these serial blocks with the when construct. So going back to this sum method, we can get the sequencing we're looking for by, okay, if some method is invoked, the first thing we'll do is execute this serial block of code. We'll execute block 1. Then we'll wait for the arrival of entry method 1. As soon as entry method 1 actually is arrived and invoked, in serial we'll execute this block 2, whatever code that might be. It could be any block of C++ code. And then finally we'll wait for entry method 2. Once that arrives, execute block 3.
So you call some method.
Right, so when this sum method...
It does block 1, and then it just sits there.
Right.
Waiting for someone to call entry method 1 and complete entry method 1. And then it will do this.
So, and this is essentially the definition of entry method 1. It now treats entry method 1 as a message. When it sees that message, this is the code it executes.
Usually there'll be some data. So some char.
I think my question is far simpler. Like entry method 1 is some other method declared somewhere else?
No, it's declared right there.
It's,
No, it's a very valid question.
Yeah.
Sorry for
The name doesn't actually.
Block 2 is not the entry method 2 code, right?
Right.
It is pretty much acts in this case as if it's entry method 1's code, right? And block 2 is entry method 1's code is what it appears like, but in fact entry method 1's code is deep inside the bowels of this structured dagger system. It automatically generates the code. All that you do is somewhere else in your program you declare in the declaration of that object in the .ci file you put entry method 1 parameters semicolon forward declaration of it.
Yeah.
So you are giving away the right to write the code for that method to the structured dagger runtime system. And all that you're saying is, because it could be when entry method 1, comma, entry method 5, serial block 2, right?
Right.
All that it is saying is, follow this sequence that I'm giving you here. I don't know if that answered your question.
No, my question is much more elementary.
Okay.
My question is, like, go to the next slide.
Yeah, it might help when we actually see
What does
the...
that even mean? Wait for entry to arrive. Like, this is some other method. Like, you're hanging there waiting for some other guy to do
Well, so
something.
imagine, so
No. It's not anyone else waiting. Go ahead.
yeah, so imagine that any entry method, SDAG or not, is essentially a receive operation by that shard for a particular kind of message that matches that method.
Yes.
So normally those receive operations are a wildcard for the whole object, and they're going to, the runtime system is just going to pick one and give you a message that fires one off. This says, for this particular kind of method, I'm going to post blocking receives for that method. And the only time I want to execute something that accepts one of those messages is when I see a block of code like this that says, when I get this message, do stuff. And correspondingly, if you see that, or when the runtime system sees that, if it doesn't have a message, that means the object's control flow is blocked. So it's just going to return to the scheduler and stop execution at that point.
Okay, so it's going to, you call some method, you execute block 1,
And at that point, you return control to the scheduler.
You no longer become one.
Return control to the scheduler, but it remembers that you were here.
Yes.
But then some other entry method in some other place on some other char gets called entry method 1.
No. Something calls that on this
On
object.
you. Somebody invokes that method on you.
Oh, so it's another entry method in the same char.
Yes.
Yeah.
Yeah. So
Okay.
they sent you they sent you a
It's called
message
entry method
for
1. It's not called some method, right?
Yeah, something calls entry method 1 on this chart.
Char, and it executes entry method 1. It completes it.
It executes this code. It executes the code right here. This is the implementation of entry method 1.
Yeah, it might become a little more clear
Okay,
when we
thank
see the
you.
whole file. But basically, this char has, as far as we can tell, 3 methods that can be called on it. A char can send it a sum method, or it can call some method on it, entry method 1, entry method 2. This is just saying, okay, if we get entry method 1, somewhere out here, we're not going to execute that. But if we get some method, we'll start here, execute this, and we'll wait for this message to be available, then we'll wait for this message to be available.
So if I called entry method 1 before some method, I wouldn't have to do it again. It would
Yeah,
remember
Right,
the
it'll just end up buffered saying, I can't execute it this time.
Just semantically was incomprehensible to me.
Yeah.
Okay, so a little more on the when construct. So again, you have these when constructs saying what method you're expecting, what parameters it's going to receive, and then it'll execute whatever's after that. You can also essentially chain these together. So if you're saying, I don't want to move forward until I receive both my method 1 and my method 2, you can just have when followed by a comma. So now the runtime system, when it receives method 1, if it still doesn't receive method 2, it'll still return control to the scheduler. And then once basically all of these dependencies are satisfied, then it will say, okay, I have all the methods I need. I can continue with whatever I was supposed to continue. Which again is just the same as when my method 1 is called, again, wait for my method 2.
Oh, actually, there's a typo on there. That further code in the third thing should be inside the inner braces.
Yes,
And that's important because that's a lexical scope.
Yeah.
Param 1, param 2, and param 3 are actually in scope inside those braces, the same as they are inside further code in the second listing. And presumably, if you were waiting on those methods to be executed, then it's because you were dependent on the data that they contained.
And instead of further SDAG in the comments, it should be further code.
Yes.
So let's see. Oh, yeah, so structured dagger can be used in any normal entry method, excluding a constructor. It can be used on a main char, a char, or an array. And then there's just a little bit of extra you need to add when you have structured dagger code. So again, this is going to be in the CI file. So code for this structured dagger stuff is going to be generated by the charmc translator. It'll generate a macro that you need to include in your actual C++ file, so it knows what extra code to include there. And it also adds a little bit extra to the pup method. You need to also call SDAG pup. So any SDAG state information and stuff like that can be pupped as well. So now, yeah, okay, so this is an example. Again, just here's what the CI file would look like. If it has some entry method with a body, then we have structured dagger code here. In the CPP file, we just need to make sure to put this at the top so it knows to include any SDAG code. Okay.
And just can you flip back for just a second, since we said we'll call out placeholders. So the name of that macro has the class name for the corresponding class stuck onto it.
Yep, so in this case, the class name and char is declared as myfoo, so it's myfoo underscore SDAG code. Okay, so now we can actually get to a concrete, this is the Fibonacci example. Again, it's in the code directory. So in this case, we have the constructor, which doesn't do anything special, so that's going to be defined in the CPP file as it was before. And now we have this sort of driving calc method in the SDAG portion. So in calc, we receive, what Fibonacci number are we supposed to calculate? N. If n is less than our threshold, so this actually also ties in some of the grain size stuff Harshitha mentioned. If n is less than some threshold, then in serial, we'll just compute the Fibonacci sequentially and respond with that. Otherwise, in serial, we will create our 2 children chars, and then after we create them, then we just wait for 2 responses. So we wait for some response that will send us a value and some response that will send us another value. And once we've received those 2, we can respond to our parent with the sum of those values.
Can you explain like why, what, like in the threshold line, n minus less than threshold?
Mhm.
What does that serial do for me?
Um,
How does it modify anything? I mean, I don't know.
so respond is actually going to be just some other method that is defined on the Fibonacci class, which we'll look at shortly.
Yeah.
So is sequential Fibonacci. So all this is saying is call this sequential Fibonacci function with n, since we don't want to continue recursing too far, and pass whatever result you get. So respond is just the method, as we see, that just sends your result to your parent. So here we're saying our result can be computed sequentially and take that result and respond or send that to our parent. If we're not below threshold, then our result is going to be computed basically by our children. So we create two children. When we receive both responses, now we respond with our parent instead of with the sequential computation, just with the sum of the two subproblems that were solved by our children.
What does the word serial do in this context? That if it wasn't there, it would do something different.
It's a signal to the parser that everything in the following block is C++ code and not SDAG.
Yeah.
We don't.
Okay.
Parsing in C++ is hideously
Okay.
painful, and no one gets it right, so we don't try.
Okay, sorry. So serial is.
And again, this is sort of, and this might be sort of related to your previous question, is here is also, we're saying that this Fibonacci class, it has a calc entry method, and it has this response entry method. It just so happens that the response is used in the SDAG code. So the response entry method takes some int, and when it's called, if we're ready for a response, it'll trigger these when blocks.
Now, if that wasn't in serial and there was some parallelism to take advantage of, Charm would have exploited that.
Which part?
Like the respond or sorry, if there had been several lines of something like either like multiple responds, those could have gone in parallel or something.
So at this level of sophistication, there is no intra-char parallelism. Does not exist.
Oh, okay.
Chars are sequential objects.
Okay. So the serial just really just.
The serial really is just a signal to the parser.
Yeah, it's just saying execute this block of code sequentially as you would any other block of C++ code.
Yeah.
And eventually you may add a parallel block.
Not like. Well, so there's a separate construct overlap, which
Is coming up.
it's in here, okay, which says there's multiple things that might block, interleave them. But even then, the execution semantics are still sequential within the char.
Yeah,
only one of those will be executing at a time.
It goes back to like the original semantics of our entry methods. We want those to execute, when we are executing entry method, we want that to be the only thing we're executing sequentially from start to finish without preemption, because that's our basic unit of computation.
Oh, without preemption.
Right. So this is the same type of thing. When it hits a serial block, this char is going to be executing until it finishes that serial block. Then it might be.
It could go and do just giving up control of the run.
Yeah. Then it'll give control back to the scheduler if there's something left for it to do.
Yeah, so you can write that code with full confidence that doesn't need to be reactive.
Ah, okay. All right. So I can declare static something or other and all those bad things that you shouldn't do.
In the previous examples of code, like the real class methods were in the C file or C++ file. Now they're migrating into the CI file.
Yes.
So in general, yeah, basically the SDAG is going to model the control flow, and that's going to stay in the CI file. And then the implementation of the guts sort of will usually still end up being in the CPP file. So like we don't have the actual definition for sequential Fibonacci and respond here. Those are going to be in the CPP file or the C file, which we'll look at next. This really just is to lay out the control flow in an easier to read way. In the previous example, it wasn't actually clear why. Okay, why did you create two new children? When are you going to respond to your parent? What's the deal there? Here it's very explicit. You either respond right away, or you create two children and wait for them to respond, and then respond to your parent in turn.
That's a stylistic choice. We're recommending that you keep the code here in the CI file to the control flow and call a function which does the guts elsewhere. You could actually put any arbitrary amount of C code there.
Yeah, that's what.
Yeah, the idea is it's especially as you get more complicated examples, it's nice to be able to look at the CI file from a high level and say, okay, these are the steps my code is going to take in this order with this control flow, and then we need to know the guts of, for example, sequential Fibonacci or respond if those are even more complex. Then you go and look at the C file and see what the actual implementations of those things are.
Because, like something like OpenAtom,
Yeah.
flow of control is nowhere. It just, you have to read the code to know the flow. And so it's been SDAG.
Yeah.
So that's not true. I tried some of these RTH files that sort of did that. That was what was available when we started. And I think this is good because otherwise you give the code to a physics postdoc. And they're like, main ends. What happened next?
And then, so yeah, here we have the associated CPP file, which again is in the code directory, and you can compile and run this. But here it just includes basically the basic units of computation here in the Fibonacci class are how, once you reach threshold, how do you actually just sequentially compute Fibonacci? And this is just done recursively. So to compute n, you compute n-1 and n-2. And the respond is just if I'm the root, if I'm not the root, I'll respond with my value to my parent as I was supposed to and delete myself. Otherwise, if I'm the root, it's the end of the computation. I spit out what the Fibonacci number is, and then I exit. So here we don't. So we take basically all the control flow that was implicit in the original example, pull that out, make it very explicit in the CI file, and then all that's remaining here is sort of these atomic units of, okay, how do you respond? How do you compute a sequential Fibonacci?
So to the untrained guy, calling seq fib with n-1 looks like a function call, but it's actually a char invocation.
No, this is a function call. This is just a regular C++ method. Especially if you look at the CI file, the only entry methods for the fib char are calc and response. So everything here, these are just local methods. They're just like any other method for a plain C++ object.
Oh, I see. So only two children are created, n-1,
Yes.
n-2, and each one of them just does a local copy.
To a point. Basically, so this goes back to the grain size thing. So when you start at the root, if the n is high enough, you'll create two children. Each of them will create two new children. Eventually, they're going to get to a point where they say it's just silly to keep creating more children because the computation is getting very, very, very fine-grained. So at that point, then they'll take over and do the sequential computation. For example, if the threshold was 5 and you wanted to compute the Fibonacci of 10, you would have chars for 9, 8, 7, 6, and 5, but then the 5 char would take care of actually computing the Fibonacci of 5 just sequentially like you normally would in just any other C++ code.
Looks like you have a code duplication here with the parallel logic on this.
Also, you're never going to call. Are you ever going to call seq fib with n larger than 2? Because
Yeah,
it keeps spawning children.
Threshold is 10.
Yeah, so in this case, we've defined the threshold to be 10, and if you look at the control flow, we only, if n is less than threshold, so if n is 9, 8, 7, etc., that's where we'll call this sequential Fibonacci and actually do the computation there and respond. Otherwise, we'll create children. So it's either you've reached the threshold and you do the rest of the computation yourself, or create children.
And yes, there is that duplication between the sequential and parallel code.
So is there a way to get rid of this duplication? So maybe compiler could compute your sequential code or chart from the parallel one?
So for sophisticated applications, we have a framework that uses recursive char construction for, I think, state space search applications, where you give it the logic once and it synthesizes both versions. But for the most part, this kind of thing doesn't actually come up in real applications. So it's an example code just to show the mechanisms. It's not something you would actually do.
Okay, so back to the when construct. We can use this for more complex sequencing. The Fibonacci example was very straightforward. Wait for 2 messages, respond to your parent. In this case, we have a much more complicated sequencing. Here we wait for method 1 to happen, and then we need to wait for both method 2 and method 3 before we continue, and then after that, we again wait for method 4. So you can basically define these arbitrary orderings of waiting for methods, blocking until you receive them, doing the correct computation, and then moving on with whatever you're supposed to continue doing. So again, this just goes through what I just said. You wait, and then once you receive the messages, you continue. So again, here, if method 4 arrives first, the method will just be buffered by the runtime system, and then only when it's ready to be executed will it actually be called. We can also use when to wait for reference numbers and get even more complex with the when. So for example, here if we're doing something where the first parameter of our method is an integer, we can say, okay, we specifically want to wait for this method call where the first parameter is integer. So then here we do the serial block and send it 2 invocations of method 1. The first one doesn't match the when, so it won't be executed, and this one does match, so it will be executed. So you can do this, for example, to make sure iterations happen in the correct order. If you pass the iteration number as the reference number, then you make sure that if you have information for iteration 2 and 3, you'll do iteration 2 first, for example. It also provides a lot of control flow constructs that you'll see in C. So you can have if then else in the SDAG code. So if, in this case, if we're the 10th or the 11th char in the array, we'll wait for this method. Otherwise, we'll actually wait for a different method. So you can actually change, so you can have the control flow dependent on fields in the char itself. Similarly, you can have for loops. So for example, here we're doing a bunch of iterations in what looks probably like a one-dimensional stencil code. So in every iteration, we're going to wait till we receive the left, then we'll compute whatever we had to do with the left data, wait to receive the right data, do whatever computation we did there, and then go to the next iteration. And here again, here we see this messages tagged by the iteration number. So if, for whatever reason, the guy to my left gets too far ahead and he ends up sending me information from an iteration that I'm not at yet, it won't match this message. So you will just wait for the left from your particular iteration, compute it, right, compute it, go to the next iteration. So it makes it very explicit what the computation flow is supposed to look like, and then the actual guts of the computation, you would usually, again, you could put them all here in straight line C code, or what we suggest is making it just a separate function you call.
Is the for construct blocking for each iteration?
The construct itself isn't necessarily blocking. What causes it to block is these whens. So it'll enter the first iteration, and then, again, if there's no message here, that if it's expecting this receive left message and it's not there, it's going to return control to the scheduler, and once this message arrives, then it'll wake this char up.
This will enforce strictly. You do left, right on 0 before you do left on 1.
Similarly, we have a while construct. So, just like we have for loops in C++ and while loops, we have while loops in SDAG as well. Here we just have something where
you can
every
skip
iteration.
through the body.
Yeah, it's pretty straightforward.
The construct, it works the same as before. We're short on time. So.
Okay, so overlap is a construct that it starts getting a little bit more interesting. So by default, it defines a sequence that is followed sequentially. Overlap allows you to add a little bit more uncertainty and asynchrony into the when blocks. So basically, or well, any SDAG construct. So overlap can let you adaptively overlap these blocks. So for example, here, we know that we want to do block 1 first. And then we know that before we do this block 5, we need to do blocks 2, 3, and 4, but we don't care in which order we do them. So this overlap will say, okay, maybe entry method 1 is, or entry method 2 is here, but entry method 1 is not, but we're in an overlap block, so we can do this first, then maybe we do the serial, then we do this. We just do whatever work is available while still enforcing some kind of ordering, so we guarantee that block 5 does not execute before all its prerequisites have been met. Just another example of an overlap where we can go down these 2 chains and interleave basically, and once they're both finished, that will likely be the end of the computation. For all is another kind of loop with do-all semantics. It's basically a loop in which the iterations can occur in any order. So you know you want to do some computation this many times, you just don't care in which order each iteration happens. There's a parallel prefix example in the tutorial code. We can probably just gloss over that. It allows you to pull up for when you pass a value, all the control flow is just made explicit. So depending on what stage of the prefix you're in, you will send your value to your neighbor, and then you will wait for the appropriate value from your stage to arrive, increment your value, and then after you've gone through all the stages of the parallel prefix, you'll contribute to the done. And again, with this asynchrony, For example, if you're near the end and you don't have as many stages to compute or to actually send values for, you do this, and then when you get to contribute, that'll happen asynchronously. So you'll contribute that you're done, and while the other chars are not done, they can move along while you're just sitting there idle. And with over decomposition and asynchrony, that will all happen asynchronously.
Those quotes around like there are different phases in the done and the sim value. That's just
Right. So this is tagged. So like when we do the performance, for example, when we look at projections views, it will tell us like, oh, this is much time was spent in this entry method and this entry method.
Oh.
Now we can break it up. You know, if we do serial, we might want to see, oh, how much time was taken in this serial block of code, and that will show up in your projections reports. Again, iteration. This very clearly can lay out iterative codes using for loops and blocking in each iteration for the messaging that you need.
Yeah, I think we're just going to have to skip over.
It is pretty much what we saw. You have the exchanges at each side, and in each loop, you wait for your exchange and you compute the data, and then move on to the next iteration. Remember what was this trying to show? What was the
Just that you
big
could
point?
set up a whole bunch of requests and then wait for the responses.
Okay. Oh yes. Okay. So yeah, in this case, you know your key is, the value for the key is stored somewhere, so you send the message there, and then you just wait for those values to come back. You don't care where they're coming from. You just know that you sent out, for example, n requests, so you're expecting n responses, and as you get them, you'll store them in your own local data.
Okay. So I'll pick up here.